Okay, so today we start very important, but in my opinion, very challenging topic. This is very typical and no for C and C++. So I'd like to tell you something about pointers, and then, not today, but next week, about dynamic data structures. In languages like Python, Java, or JavaScript, there are no pointers available. So every value, every variable is represented as a numeric value, or as a text, or as a list, or something like this. In C++, we have access to deeper part of computer, let's say. So we are able to manage how variables are represented directly in memory. So using this method, we can get higher flexibility, or we can optimize something. Yeah? But all issues I mentioned today are are true for all programming languages, but in some programming languages these elements are not directly accessible. Okay, so first I'd like to start from start from memory organization. So I told you that everything which is stored in computer has to be represented as a string or set of bits. So memory in computer is organized in bytes. So the byte is the smallest amount of memory we can address. So the smallest amount of memory we can get access. So of course, byte consists on 8 bits, but we can read at least 8 bits. Frankly, in 32-bit architecture, we can read at least 4 bits. In 64-bit architecture, we can read at least 8 bytes. Sorry, 8 bytes. So, but from the perspective of programming language, the smallest amount of memory which can be addressed, so read, is 1 byte. And in computer, every byte in memory has unique index. So the index of this cell is called an address. So here, look, you have example. Here is memory. So memory is one-dimensional array, and every cell in this array has unique address. Addresses are similar to indices in matrix, so in arrays, so in C. So they start from 0 up to the value of the the largest, so this value, the final value represents the last byte. So the highest address represents the amount of memory we have access. Of course, this is a little bit simplified because in fact, every process, so every application has its own address pool. So in fact, there are no so strict correspondence between address in RAM memory and address of particular cell in our app. But okay, we will be talking about this issue later. But look, if we have, for example, integer variable, it takes 32 bits. Yeah, so it gives 8 bytes, 4 bytes. So it means that it has to take for subsequent cells of the memory. What else? Oh, okay, I haven't mentioned that address is integer value, so it's value from 0 up to, you know, the maximum. For 32 bits architecture, the address has 32 bits. In 64 bits architecture, the address has 64 bits. So what does it mean? It means that the number of combinations, so having 32 bits, the number of combinations, so the number of different addresses is 2 to power 32. So do you think that it is large value or not? So is it enough for us to have 2 to power 32?
Yes. But maybe in 10 years it won't be sufficient.
Sorry, but
it is not sufficient.
Yeah, of course, because
it's only 4 gigs or so.
Yeah, it is only for 4 gigabytes. Yeah. So okay, you can see that it's not enough for us now. Yeah, because most computers has more memory. If we have, for example, if we have only 2 gigabytes of RAM in our computer, this memory can be extended by using swap on your hard drive, for example. But if we have only 32 bits, the swap, so the random access memory plus swap file are limited to 4 gigabytes. So this limit can't be, you know, extended. In 64 bytes, we have 2 to power 64 different addresses. So it's much more bigger value, yeah, because it's not bigger 2 times, but it has to be squared, yeah. I guess. No, not squared. Sorry, it should be. So here we have 4 gigabytes to power 32. So this is the amount of memory we can address in current computers. Yeah? So for now, so now it's almost impossible to have so many RAM or RAM plus swap. So it is enough. Okay. Now look, if we have a variable, integer variable, it occupies 4 subsequent bytes. But look, if the variable looks like this, we have to split this value into parts, and every part should be, written inside different to different cell. There are 2 possibilities. So look, I have variable a in hexadecimal form. It is FFEEDDCC. So one possibility is that the least significant byte will be the first one. So we have CCDDEEFF. The other possibility, how we can, write it, is CC DD okay, E F. And the way how variable is, split into memory cell is determined by processor architecture. So for computers which works in x60 okay, sorry. For processor you have in your computer, so for Intel or AMD family, the organization is like this. It is called little endian. But in some server processors like Sun or Spark, the organization is different. They are represented in opposite order. So the bytes are organized in opposite order. And this organization is called big endian. Why so strange names was given? The names, okay, this issue is called endianness. And it is originated from Gulliver Travels. I don't know whether you have you read this book, but in this book, Gulliver visited an island where Lilliputs lived. Okay, there is, and there were 2 political biases. One of them, called Little Endian, thought that or believed that the egg should be eaten from this sharper end of yeah, and the other bias was that the egg should be eaten from this thicker part, and they, of course, there were some problems between them. So so it was taken from this book, but here it means that the byte organization is different. So what are the consequences of endianness here? Look, if we have the value which is organized in little endian manner, and we dump memory, so I copy memory byte after byte and paste it into the memory of for example, big endian architecture, we get the same byte organization, but it means that in case of big endian, if I have the memory which is represented on this way, the value of the element will be CC, DD, EE, FF. So this value is totally different than the value of A. So whenever we move data between two different systems, we have to preserve that the endianness doesn't influence on the value. Okay, so for us, I will tell you something about this when we will be talking about computer networks, but this is very important issue regarding portability of data. Looking at the car value, you can see that it occupies only a single byte, so there is no difference between little and big endian architecture. The same if we will have a character array. So in every cell we have a single character value. You can see that the endianness doesn't influence on it because, okay, they are separate characters. So every value is stored, in a single cell, but they are grouped in form of array. Okay. So this is the way how variables are represented. But in C and C++, we can create a variable of type int asterisk. So this type with asterisk is called pointer type. So what is the difference between int and int asterisk? Int stores integer value. Int asterisk stores address. In fact, I told you that the address is also integer value, but the size of a pointer depends on the compiler architecture. So if you use 32 bits compiler, the int asterisk has 32 bits. If you use 64 bits compiler, the pointer occupies 64 bits. So in fact, we can create a variable, let's say P1, and variable P1 occupies 4 or 8 bytes of memory. And this variable is dedicated for storing address of integers. Here we have float, asterisk. So again, this is the address. So it takes 4 or 8 bytes, but it is dedicated to store address of float variable. And here we have address. It again takes 4 or 8 bytes, and it is dedicated for storing address of character. So look, there are no difference in size of pointers, but now I'd like to explain why we have so many different pointers. Even there are no different memory space for ints, floats, chars, because we have memory, and in memory we can allocate place for integer, for float, for character, etc. But we store them in the same memory. So why we have so many different types? Let's try to analyze this example. So look, if we have a variable a, this unsigned integer, and now I have pointer to integer. And there are two operators related to pointers, which you should understand. Sorry. So the first is ampersand. So the ampersand reads the address of variable. So this operator returns address of variable a. So whenever you write ampersand variable, you get the address. So for example, here we have variable a, and I write ampersand a, so it returns the address of the variable. You can see that this variable occupies more than a single byte, but the address of variable means the first address of the first byte. So in this case, if you use ampersand a, the value of this expression is 1002. Of course, this is an example, no? But let's say that a address is like this. So in this case, the 1002 is printed into the, or is written into the this area of memory. So it is assigned to P1. So now the value of P1 is 1002. So whenever you want to read address, you should use ampersand. Okay. Then we have the second operator, asterisk. Okay, Mr. Daines, I will answer your question at the end, okay, of this lecture. Okay, so look, the dereference operator, so asterisk pointer, so using asterisk next to pointer, it means that I'd like to refer to a value which is stored under this address. So in this case, when I write asterisk P1, I mean value of A. Okay? So if I write asterisk P1 is equal to, in fact, it is equivalent to A equal to. About terminology, if I assign address of A to P1, I can say that P1 points to A. So it's pointer to A. So if it is pointer to A, asterisk P1 is a reference to A. So in this case, whatever you do using asterisk P1 will affect the value of A. Because asterisk P1 and A are equivalent, so they get access to the same area of memory. Here you have the okay, it's so it equal to all memory. Yeah. If you write asterisk P1 equal to, it look 2, because integer occupies 4 bytes, the value of 2 for this integer is like this. So the most significant byte is 0, the second and the third byte is 0, and the least significant byte is 0.2. So in this case, when you write asterisk P1 equal to, it means that we have 0, 0, 2, 0, 0, 0. So if you have the asterisk integer pointer, it will affect not only on a single cell, but it will affect all cells. So all memory cells will be modified. Okay, look, here we have example with character. And when I have pointer to character, I can do the same. So now P2 points to the Z. Yeah? So it points to the cell 1009. And again, using the reference, will modify the cell here. So here, the ASCII value of A will be printed. So now I'd like to tell you why we have so many different pointers. Look, the pointer type, so char, tells the compiler how to handle the dereference operation. So if we have pointer to char, only a single cell will be modified. If we have pointer to integer, 4 cells will be modified. If we have, for example, pointer to float, again, 4 cells will be modified, but the value will be represented not in this way, but it will be represented as the base and exponent manner, yeah, as floats are, yeah. So so the pointer type defines how values will be, handled or splitted inside the memory. Okay. So look, here we have very simple assignment. So let's say that we have the program like this, and then we want to answer four questions. So the first question, what is the value of P2? What do you think? Of course, you should consider this example. No. The value of P2 is address. So the value of P2, if you have the notation like this, P2 is equal ampersand Z, it means that value of P2 is address of Z. So not 32, but 10009. What is the value of ampersand Z?
Also the address?
Yeah, of course. So in this example, 1009. What is the value of Z?
The memory cell?
No, but okay, everything is memory cell, even pointer.
Ah, okay.
But what is the value of, so looking at this example, what will be the value of Z? So if you write C out Z, what will be printed?
0.
Mm,
0, but the character. So
character.
32.
So precisely, not 0. 0, it was 0 here, but we performed several operations. So we write the reference P2 is equal to A. So look, the reference P2 has access to this memory cell. So it overwrites with A. Huh? So the value of Z will be modified, not using the operation Z is equal to A, but using pointer. But this is because P2 points to Z, this operation is equivalent. So this operation modifies also the value of Z. So the value of Z is A. Yeah? What is the asterisk P2? So what is the value? No, asterisk P2, look, it is the reference. So if the pointer value is 10009, so it means that it points to the memory. So the asterisk P2 is the same like Z. So it is, in this example, it is equal to A. What's more, value of P2 and ampersand Z are the same. So these values are equal, yeah, because they were assigned in this place. Okay. So now we have another example. So look, again, we have the first 3 lines are the same, but in this line we have asterisk P2 plus plus. So what does it mean? So what will be the final result? So what will be P2? P2 is pointer, yeah? So it stores address. So what will be the address of P2? No, not address of P2, value of P2. Yeah, it will be 1009. By the way, what will be the value of ampersand P2? Ampersand P2. What? Yeah, F006. Ampersand P2 is the address of the first byte of P2. Yeah, so address of variable P2. Okay, so ampersand Z will be the same like P2, so it will be address of Z in memory, so it will be 10009. What will be the value of Z when we perform the operation like this? So look, first we should to think what does it mean ampersand P2 plus plus. Not ampersand, the reference P2 plus plus. So look, the reference P2 is the value in this cell. So it is a reference to this cell. Yeah? So if you write the reference P2 plus plus, it will get the value from this cell and increase it by 1. Of course, these braces are not important. You can use it or not. Yeah? So, okay, Mr. Mikołaj, you're right. It will be 1. Yeah? So, because 1, okay, 1 not numeric value 1, but character 1. Yeah? So this will modify both the asterisk P2 value and Z value because they share the same area of memory. Okay, so here you have asterisk incrementation of the reference. So if you increment the reference, it will affect the value of element or cell which is pointed by pointer. So for example, if you have P1 which points to A and you write P1 plus plus, it will increase this value by 1. So probably this is the least significant byte. So increasing by 1, this value will be 0xCD. Yeah? I guess all remaining cells will be the same because we increase it only by 1. Okay. The second possibility of incrementation is pointer incrementation. So for example, P2 plus plus or P1 plus plus. What does it mean? It means that we want to increment the value here. But incrementation pointer works different than incrementation of standard integer value. What is the difference? The plus plus operator or minus minus operator means go to the next element. So for example, if we have P1 and its value is 1002 and I'd like to increment it, this value will be changed not to 1003 but to 1006. Why? Because the size of character is 4 bytes. So in this case, the size of variable is added. So the pointer points to the next value. If we increase by 1, it means that our pointer will point our variable starts somewhere in the middle. So it makes no sense. So remember that for pointers, plus plus minus minus means go to the next or previous element. Of course, having pointer to char, and if you increment the P2 it increased the address by 1. So because the character size is only 1 byte. So in this case, you get 100A. Yeah? So we increased it by 1. So our pointer will point to the next cell. And remember that if you change the value of pointer, it doesn't affect the values of pointed variables. So it doesn't affect the memory here. Yeah? So it only modifies the value of pointer, not the values which are referenced. If you, for pointers, you can use also plus and minus operators. And again, plus k or minus k, it doesn't mean increase by k, but move by k elements forward or backward. So pointer plus 1 means increase for integer, increase by 4. Pointer by 2 means increase by 8 elements. In case of character, it means increase by 2. Yeah. So the pointer type determines not only the way how we should handle values. So if it is float, we should represent values on different way than for ints, but also it determines what the behavior of the arithmetic operators. So the number of bytes which will be, moved when you add or subtract value. Okay. So sometimes there are some on quizzes, there are some assignments. What does it mean? Or what is the value of P1 when you add 1? Oh, okay. And you have to consider the type of pointer and write proper answer. When I told you something about functions and type of arguments, I mentioned about reference. So now I'd like to look more, to spend some time for talking about reference. So look, here we have a piece of code, and here I have variable A, and now I have variable B, which is integer, but it is integer ampersand. So this type is called a reference. So what does it mean? It means that B is a reference to A. Practically, it means that A and B are located in the same area of memory. So whatever you do with A will affect the value of B. Whatever you do with B, it will affect the value of A. So the same like in functions with reference arguments. So look, if I have two pointers to int and I read address of A and address and to B, the question is, so P1 points to A, P2 points to B. The question is, what is the value of P1, the reference? Do you have any idea? 1. Okay. What is the P2, the reference? So asterisk P2. Also, yeah? Because A and B shares the same area of memory, so they have the same address. So look, P1 and P2 has the same values. Yeah? A and B also has the same values. It is equal to 1. No. So if you modify, for example, you write A is equal 5, it will affect B because B will be equal 5. P1 will be asterisk P1 and asterisk P2. Both of them will be equal to 5. If you modify asterisk P2 equal, let's say, 8, it will affect A, B, asterisk P1, asterisk P2, because all of them share the same memory. Remember that if you create a reference, you have to initialize it always. Yeah. So if you write, for example, int reference x, the compiler will throw error. Yeah. So it is impossible to create a reference without initialization because the compiler doesn't know where this variable should be, located. Okay, so now I'd like to verify whether you understand how pointers works. It seems to be a quite, academic example, because you may think, okay, what's going on? Why I should use pointers? I like to show you some application pointers later on, but to use it efficiently, you have to know how pointers works. So this example is not practical, example. So there are no real code like this, but it led us to understand some dependencies, and it will be easier to follow examples later on. Okay, so look, the initial code is like this. So I have two variables, A and B. They are independent variables, so they store values in different area of memory. I have also variable C, which is a reference to A. So A and C shares the same area of memory, and I have two pointers. So initially P1 points to A and C, and P2 points to B. And there are, so after every line, I will ask you, what are the values? A, B, C, asterisk P1, asterisk P2, P1, P2, ampersand, ABC. Okay, here we don't have the absolute addresses of, for example, of variable A, but we can tell that value of P1 is equal to, for example, value of ampersand A. So these two values are the same. Or value of P2 is equal to value of B. Okay, so this is the proper answer related to pointers. If there are questions about values of variables, okay, we should use the real value here. So now, in the initial case, we have A, B, C. So A and C are 2, B is 3. The reference P1 is the value in the cell which is pointed by P1, so it is also 2, and the reference P2, so asterisk P2 is equal to 3. So look, now we perform this operation. So asterisk P1 is equal to asterisk P2. What does it mean? So what is the value of A?
Is
3.
it 2?
Yes. And B?
3?
3. Okay. So look, asterisk P1 equal to asterisk P2. We can write that asterisk P1 equal to asterisk P2 is equivalent, for example, to A equal B or C equal B. Huh? So they are equivalent because asterisk P1 is the same like A or C, yeah? And asterisk P2 is the same like B. So it will be easier to interpret this line, especially when you start your adventure with pointers. If you substitute, virtually substitute the real variables instead of the reference. Yeah? So look, the real effect will be that the value which is written in this cell will be override. So it will be equal to the value of B. Okay. So look, now I have the next line, B++. What is the value of A now?
3.
3. Value of B?
4.
4. And value of C?
3.
3. So look, if you increment B, it will affect only this cell. So it affects B and affects asterisk P2. It doesn't affect this block. Okay. So look. Okay. Now that is the very yeah. I have P2 equal to P1. So what does it mean? What is the value of A?
3.
B?
Stays the same, yeah.
Yes. So what changes here?
P2 points to P1 now, so
Yes.
to A and C.
Okay, so look, what is changed here? So P2 points to P1. So now the value of asterisk P2 is the reference to this cell. Huh? So everything which is related to P2, so asterisk P2 or P2 value is changed. Other elements are stay the same. Okay, asterisk P2 plus plus.
It will go back to B.
No, it's the pointer, so it's the value.
Is
So the value
pointer.
goes up. Yeah.
Okay, yeah.
So here we have the reference, yeah. So it will affect this cell, yeah. So it will be 4, yeah. So everything which is related to this cell, so asterisk P2, asterisk P1, A, B, C will be 4, while B will be 4 too, but you know here they are not dependent. So now I have C++. Okay, so if you use C++, what will be the the final value. Oh, okay. I'm sorry. Okay, what will be final value? So what will be A, B, A when you perform C++? Yeah,
Since
Will it be 5?
5. It will be 5. So A, C, asterisk P1, asterisk P2 will be 5, while B, okay, will be still 4. Yeah. So
okay, so where's kind of different because you'd think because C is a reference, right? It's a reference to A.
yeah.
So it doesn't really work like a pointer because if you would increment a pointer, it would point to B. But
Yeah.
if you increment C, it works like a value. So
But-
it just changes the value of it.
But C is not pointer.
Yeah. That's what I'm saying. It's the difference. That's what I
but
just
look,
found out.
if you write P1 plus plus, it doesn't mean that it will be B. Okay, it will be the next 4 cells. But
So not exactly a value. Yeah.
okay, so yeah. Okay, so remember that there is a substantial difference between pointer and reference, because reference behaves the same like standard integer type. Pointer stores address, but if you use the reference pointer, it behaves like standard integer type. Okay, but only using the reference. If we don't use the reference, we directly try to get access to address. So we modify the address of pointer, so value of pointer. Okay, so for those who don't catch this issue, I suggest you to follow these examples and try to, write on piece of paper. So try to rewrite or by your own. So you should, having the application like this, you should analyze which variables share the same area of memory. You can visualize it using boxes, and then analyzing code line by line, you should update the values which are stored. So it's easier to understand how pointers works, what are the relationships between them and some dependencies, especially when you do something like this. Yeah. So you write that the value of P2 is equal to P1. So the P2 and P1 points to the same area of memory. Okay. Okay, so now I'd like to go to the more practical applications of pointers, because it was only an introduction to show you how pointers works, what are the pointers, and so on. So first, I'd like to explain what is the relationship between pointers and array. So look, having array like this, so I have float tab of 5 elements. We usually write tab index I. Yeah? So tab index 0, it refers to the first element, so I can modify it. But in fact, the sole variable name, so without index, is a pointer. So when you write tab, in fact, it is the pointer to the first element of the array, so to the first cell. So if the address is k, let's say, the tab value is k. So using the reference operator, so using asterisk tab, you can get access to the value of the first element. So the value will be k0 here. But if you use, let's say, sum, so you use tab +1, it means go to the next element, so to the element which follows the current. So it is equal to tab plus its float, so not 6, 4, 8, 12, 16. So so in this case, the address will be increased by 4. So now tab +1, the reference, will point to the second cell. Tab +4 stores the address of this cell. So it is k +16. But tab +k +4, the reference, will get access to the value of the 5th cell. So look, when you want to get access to array, it is enough to use index operator, but using pointers, you can do the same. So writing asterisk tab +I. So these two forms are equivalent. This form may be equal or faster than this one. It depends on how index operator is interpreted. Sometimes index operator generates calling of external function. In this case, there are no function calls. So regarding that the function call takes time, this way may be a little bit faster, but okay, most compilers can handle with it and do it on a very fast way. Okay, so so I don't mean that you should use this form, but you should know that this form is equivalent. So now I'd like to mention that if we have, let's say, fill array function, and I passed as argument the name of array, the function definition was, okay, here I have int n. So the function definition was that the function fill array returns the number of elements, fill array is the name, and here, because I'd like to pass array, I have sol tab is pointer, so I have float asterisk, let's say, array. So this is the header of fill array function. So I pass, in fact, I pass the pointer to the first element of the array. So that was, you know, I showed you how to use it during previous lecture. So look, now I'd like to show you that we can use pointers as arguments. So here we have 3 different ways how we can define arguments. So swap. So the aim of this function is to swap two arguments. So I'd like to interchange. So I'd like to change value A and assign it to B, and from B to A. So look, the first code, we have int x and y, they are equal 3. So the question is, what will be the value of x and what will be the value of b when you run this code?
The opposite?
Yeah, inside this function, a and b, so inside this function, when we call it with 2 and 3, a will be equal 3 and the b it will be equal to. But look, here I have arguments which are independent variables. So these two variables, a and b, are not dependent on x and y, because x stores data in some place in memory, a and b the same. So if x is equal 2, y is equal 3, if the a will be equal 3 and the b equal 2, it doesn't affect the values of x and y. So there are no result, no effect which is generated outside the function. The opposite situation, we have x and y and a and b, but a and b are not standard integers, but they are reference to integers. So in this case, x and a and y and b, they share the same memory. So initially, x is equal to 2 and y is equal to 3. But when you perform this code, y will be 2 and x will be 3. So in this case, this function affects the values of x and y. Okay? Because a is the same like x, b is the same with y. And now we have this middle example. So now my arguments are pointers. So I'd like to have a and b, which are pointers. And what is done here, I take the address, not the reference of a. So look, what's going on here? I have x. Okay, so x is, let's say, 2, and y is 3. And I have 2 pointers. The pointer a points to x, and the pointer b points to y. And now I store integer values, so t is equal to asterisk the reference a, so it is equal to 2. Now equal a, so the reference a is equal the reference b. So what's going on? The reference b is equal 3. The reference a is equal 2, but it is the same to what x is. So in this situation, 3 is written here. And then we have asterisk b is equal t, so it will affect y. So it will be 2. So you can see that the final effect is the same like in the reference case. So in this case, x and y are swapped. When you pass arguments by value, the values are copied, so there are no effects outside. So now I have several practical questions. So what do you think? Which of these 3 methods is the fastest?
feel like the third one.
Third one. Okay. Why do you think so?
I can feel it in my gut.
Okay. Okay, look. So, yeah, this method is the fastest one comparing to the others. Why? Because if you have reference, nothing is copied. So if you create argument here, for example, here, you have to allocate memory for A and B, and you have to copy value of X to A and value of Y to B. So it takes time. It takes time. It allocates 8 bytes on stack. But so this will be slower comparing reference where the arguments are not copied because they are, you know, only assigned to X and Y. So no additional memory is allocated for variables, of course, because the function call takes some resources. But so nothing is here copied, and additional memory is not allocated. Okay, then we have the pointers. So look, if we have pointers, 2 additional variables are created. They are pointers. And the address is copied. So not value, but address. Okay, if we have 64 bits compiler, every address takes 8 bytes. So also it takes time to create these pointers to copy values. In case of integers, probably pointers will be slower than calling the function in this mode. But if you try to imagine that we have larger variables, so variable of types which are, you know, bigger than 8 bytes, in this case, all values has to be copied. So we have to allocate memory for, let's say, 20 bytes if given variable takes 20 bytes. And we have to copy 20 bytes. Here, always we need to copy pointers. So in case of argument passing by pointer, the number of data which will be copied and memory which will be allocated doesn't depend on the variable size. It only depends on the pointer size. Okay. To speed our program up, or function call up, we should use references. But using references, you can see that there is a certain risk that when you pass arguments, they will be modified inside the function. Sometimes, okay, we want to do it, but when we will use references for sake of performance principles, okay, sometimes we don't need to do it. Okay, next time I will tell you how we can cope with this problem, so how we can boost our function definition and preserve that the arguments will not be modified. Okay, so now I think it's time for our quiz.